Welcome to AI Peer Review. Today, we're diving deep into a really interesting paper. It's called R1-Reward, Training Multimodal Reward Model Through Stable Reinforcement Learning.
Yeah, this one tackles a pretty crucial area, doesn't it? We're talking multimodal reward models,
Yeah.
MRMs. They're absolutely essential for, training and evaluating these big multimodal large language models, MLLMs.
Exactly. And the authors make a key observation right at the start. They notice that while MRM architectures and the training data have gotten better,
Lots of progress there.
right, but using reinforcement learning RL specifically to improve their sort of long-term reasoning capabilities, that hasn't really been explored much.
That's the gap they identified. I mean, traditionally, reward modeling has focused so much on just the preference data itself, its quality, its structure.
Mm.
This paper takes a different tack. It asks, hey, we've seen RL work wonders for improving MLLMs directly.
Mm.
Can we use it to improve the reward models that guide them?
So the core idea is basically reframing the task. Like judging which of two answers is better becomes a kind of RL policy.
Precisely. It's a clever reformulation. But as they found out pretty quickly, just taking standard RL algorithms off the shelf and applying them here,
Yeah.
well, it wasn't stable.
Ah, okay. That's where the problem started.
Yep. They pinpointed three main challenges. First, limitations with PPO-like algorithms, specifically the clipping mechanism.
All right.
Second, instability coming from advantage normalization, especially later in training. And third, this disconnect you can get between the model's reasoning and its final judgment.
Right. Let's unpack that first one, the PPO limitations. The clipping is usually there to help stability, isn't it? How does it cause problems here?
It is, yeah. It's designed to stop the policy from changing too drastically in one go. But the issue arises when the advantage is strongly negative, meaning the current policy is doing poorly and the proposed policy change is large.
So the model needs to make a big jump to correct itself.
Exactly. But the clipping mechanism, that specific scenario, can actually prevent that necessary large update. Sort of clamps down too hard and can stall the learning or even cause things to crash.
Okay, so if the model's consistently making bad calls, getting negative advantage, the clipping might ironically stop it from learning effectively.
That's the gist of it.
Yeah.
Then there's the advantage normalization issue. Normally, normalizing advantage helps smooth out training, right? Keeps things scaled nicely. But think about what happens later in training. The model gets better, the rewards might become really skewed, maybe almost all preferences are strongly one way or the other.
Lots of ones or zeros, few in between.
Right. And when you normalize across that skew distribution, the few middle ground or outlier advantage values can get blown way out of proportion. Their influence becomes massive, potentially destabilizing the whole process.
Ah, so the normalization, which usually helps, can backfire when the rewards aren't evenly distributed anymore, like giving too much weight to rare edge cases.
Got it. And the third challenge, reasoning versus results. Why is that so tricky for reward modeling? Well, ideally, you don't just want the reward model to pick the better answer. You want it to understand why it's better. That's key for trust, for interpretability.
You want the reasoning to be sound.
Exactly. But standard rule-based RL, it mostly just cares about the final score, the final answer. It doesn't inherently push the model to develop a coherent, logical thought process to get there. It could guess right for the wrong reasons.
Okay, so those are the hurdles: PPO clipping, advantage normalization and stability, and the reasoning result gap. How did they propose to fix these with stable reinforce?
Right, stable reinforce. It's their refined algorithm, and it has three core modifications. First up is what they call pre-Cli-P.
Pre-Cli-P.
Yeah, it's a smart tweak to the standard PPO loss. Instead of clipping the probability ratio after you exponentiate it,
Okay.
they clip the log probability ratio before exponentiation. They constrain that log ratio within a specific range. Looks like ln 10tan3 to ln 103. It's laid out in algorithm 1 in the paper.
Ah, so they're limiting how much the log probability can change before it gets turned into that potentially huge or tiny ratio that directly hits the instability from large ratios, right?
It's exactly. Clipping in log space keeps things much more contained, preventing those numerical explosions or implosions during the update. Smart move.
Okay, that's pre-CLIP. What's the second part?
The second is the advantage filter. This is their way of dealing with that instability from skewed rewards and outlier advantage values we talked about.
Right, the normalization issue. How does the filter work?
It's pretty straightforward, actually. They use the 3 sigma rule. They calculate the standardized advantage in a batch, and then any value that falls outside plus or minus 3 standard deviations from the mean.
Gets filtered out.
Essentially, yeah. They set those outlier values to 0. You can see the formula for the filtered advantage in the paper. It just zeroes out the extremes.
So it's a direct way to stop those really large or small advantage values caused by the skewed rewards from messing up the policy update. Just ignore the outlier.
Precisely. It prevents those extreme values from having this outsized destabilizing effect. And the third component of stable reinforce is the consistency reward. This one's really interesting.
Consistency reward. This tackles the reasoning problem.
Exactly. This is how they encourage the model to not just get the right answer, but to have a logical thought process behind it.
How did they implement that? It sounds tricky.
They brought in a referee, specifically another powerful MLLM Quen 2.5 VL7B instruct.
Okay, an independent judge.
Yep. The reward model being trained has to output its reasoning steps inside think tags and its final choice inside an answer tag. The Quen referee then looks at the thinking part and the answer part.
And judges if they match up. If the reasoning logically leads to the answer.
That's exactly it. It checks for consistency. Does the thought process actually support the final judgment?
That's clever. So it's not just about ground truth accuracy anymore, but also internal coherence.
Right. And the final reward signal the model gets combines all this. The paper gives the formula. Final reward, result reward, EC1 plus Barrow 0.5 consistency reward plus 0.5 Bayer formatting reward.
Okay, let's break that down. The result reward is just, did it get the preference right?
Yeah, basic accuracy against the ground truth. The formatting reward just checks if it used the think and answer tags correctly.
And the consistency reward is weighted by 0.5 here. And importantly, it's multiplied by the result reward. Wait, no, it's added after being multiplied by 0.5, but only if the result reward is positive.
Well, the formula shows result reward x1 plus 0.5 a consistency reward. So the consistency reward boosts the result reward if the result is correct, result reward into 1. If the result is wrong, result reward is 0, that whole term becomes 0.
Ah, okay, so you only get rewarded for consistency if you were actually right in the first place. That stops it from rewarding beautifully consistent but wrong answers.
Exactly. It avoids prioritizing consistency over correctness. Accuracy still comes first, but coherent reasoning gets you a bonus. And Table 1 shows the prompt template they use to get the structured output.
Makes sense. Foundational rewards for format and correctness, plus this neat consistency bonus judged by another AI. Okay, what about the data they used for all this?
They put together a new data set, R1-Reward 200K, 200,000 preference pairs.
Where did they get them from?
It's aggregated from a bunch of existing public data sets. Table 2 lists them places like MMRLHF, RLAIFV, VL feedback, and others. They made sure to get a good balance of which answer was preferred.
Okay, a diverse base. And then they did something called a long quote cold start. What's that about?
Right, so you can't just throw an MLLM into this reward modeling task with RL from scratch. It's too unstable. You need a decent starting point.
Like a warm-up phase.
Kind of. They used GPT-4o to generate detailed chain-of-thought reasoning for all 200K samples in their dataset, basically asking GPT-4o to explain why one answer was better than the other.
And that generated text became training data.
Exactly. That became supervised fine-tuning SFT data to give their R1-Reward model an initial grounding in the task. And they did something clever here, too.
Oh, yeah?
They recorded how many attempts GPT-4o needed to get the reasoning and the final preference right for each sample.
As a difficulty score.
Precisely. If GPT-4o struggled, needing multiple tries, they figured that sample was inherently harder.
That's smart. And did they use that difficulty measure later?
They did. For the actual RL training phase, they didn't use all 200K samples. They specifically selected the harder ones, the ones where GPT-4o needed 2 or more attempts or even failed after 3.
Focusing the RL effort on the tough cases where the model had more to learn makes sense. Okay, let's get to the results. Did stable reinforce and R1-Reward actually work?
Oh, yeah. The results look pretty strong. Check out Figure 1 in Tables 3, 4, and 5. On the VL Reward bench, R1-Reward got an 8.4% accuracy boost over the previous state-of-the-art IXE 2.5 reward.
8.4% is significant.
It is, especially since they mentioned using less data to train R1-Reward. And they benchmarked it against big names, too, like GPT-4o, Claude 3.7 Sonnet, Gemini 1.5 Pro. It held its own, even beating some on certain metrics. The macro accuracy improvements were also quite good.
Very efficient, then. What about the multimodal reward bench?
Even better there, arguably. R1-Reward came out on top across all the dimensions they measured. A 14.3% improvement over the prior SOTA.
Wow, 14.3%.
Yeah, and they highlight that this benchmark is diverse and doesn't overlap much with their training data, so it suggests good generalization.
That's crucial. And the third one, MMRLHF reward bench. They said that one was harder.
It's considered more challenging, yeah.
Mm.
R1-Reward performed competitively on its own. But the really striking results came when they used voting.
Voting, like running the model multiple times.
Exactly. They generate, say, 5 or 15 different reasoning paths and judgments from R1-Reward for the same comparison, and then take a majority vote.
And that helped?
Massively. With 5 samples, voting at 5, accuracy jumped to 85.3%. With 15 samples, it got even higher, over 86%. That significantly outperformed other models on this tough benchmark.
So the model might be uncertain sometimes, but aggregating multiple independent judgments really sharpens the result. Figure 4 shows the scaling effect, right?
It does. It plots performance as you increase K, the number of samples.
Yeah.
Whether you use majority vote or in any correct strategy, performance climbs pretty consistently on all 3 benchmarks as you add more samples.
It seems to level off a bit, but clearly more inference compute gives better results.
Definitely. It shows the underlying model has potential that can be unlocked with more sophisticated inference techniques. And the ablation studies, those are really important too, Table 6 and Figure 5.
Right, where they took parts of stable reinforce away to see what happened. What did they find?
Well, they confirmed the consistency reward was critical. Removing it led to less stable evaluations and potential hallucinations in the reasoning.
Okay, so that referee is doing important work.
Very much so. They also tried using Reinforce++ directly, without their modifications, and confirmed it was unstable, sometimes collapsing during training. Figure 2 shows that, I believe.
Validating their initial problem statement?
Yep, removing the advantage filter. That made the policy loss noisier, less stable convergence. And interestingly, it also led to longer response lengths from the model, which you can see in Figure 5A and 5B.
Huh, longer responses without the filter? Any idea why?
Maybe the instability encourages more verbose, a less confident reasoning. Hard to say for sure, but it was a clear effect. And removing preclip, as expected, also made the policy loss less stable, as shown in Figure 5C.
So basically, every piece of stable reinforce, the preclip, the advantage filter, the consistency reward seems to be pulling its weight. They all contribute to stability and performance.
It really looks like a synergistic effect. They also did a direct comparison in Table 6, R1-Reward versus a standard reward model, and the MMRLHF reward model, all trained on the same 200K data. R1-Reward came out significantly ahead. It really highlights the data efficiency and the benefit of their RL approach, maybe that direct comparison scoring mechanism it uses.
That's compelling. They also showed some qualitative examples, right? These aha moments in Figures 3 and 6.
Yeah, those are great. They give you a glimpse into the model's reasoning. Figure 3 shows it making a math error, then catching it and correcting itself. Self-correction. And Figure 6 is an example where the model seems confused. Explicitly says something like, let me reread the question, and then figures it out correctly. It suggests a level of, self-reflection or reevaluation.
More than just pattern matching, potentially. Okay, let's try and wrap this up. What's the big picture here?
I mean, it seems pretty clear that this paper makes a strong argument for using RL, but carefully designed RL, for multimodal reward modeling.
The stable reinforce algorithm seems key. It directly addresses those instability issues that plagued earlier attempts with standard RL methods.
Absolutely. And the results speak for themselves, big performance gains on tough benchmarks.
That consistency reward idea stands out to me too. Pushing for coherent reasoning, not just the right answer. That feels like a really important step towards AI we can actually trust and understand better.
Couldn't agree more. It's moving beyond black box judgments. And that test time scaling, the voting strategy, it suggests there's even more potential to unlock here with smarter inference.
So this work really emphasizes that improving these complex AI systems isn't just about more data or bigger models. Algorithmic innovations like stable reinforce can make a huge difference in capability.
Yeah, the performance jumps, especially with voting, are genuinely impressive. It suggests these models can achieve a pretty nuanced grasp of these multimodal comparisons when trained the right way.
Which leads to a fascinating question for you, thinking ahead. How might these kinds of RL-trained reward models change how we develop and even how we evaluate the next generation of multimodal AI if our measurement tools get smarter?
That's a huge question. It could lead to much more sophisticated alignment and fine-tuning. If you want to dig deeper into this specific work, definitely look at the data sets they list and the benchmark details. The paper's remarks section also points to related RL work on LLMs that gives broader context.
Good suggestions. So as you keep track of this incredibly fast-moving field, It's worth remembering the power we see here when different approaches like RL and multimodal understanding come together in innovative ways.